Okay, welcome to the second part of our lecture on part 1 of lecture 18. We're defining our rotational terms. All right, so let's put some of these rotational terms and definitions to use. And that's what we're going to do with example 1. So in example 1, we have a rigid disk of a known radius of 1.5 meters that starts from rest and spins about a fixed axis, right? And that's going to be the case of all our rotating objects. Its angular velocity is given as the following time-dependent equation. And then we're asked, what is the angular position as a function of time for the disk? And what is the angular acceleration as a function of time for the disk in part B? And then finally for part C, what is the translational acceleration as a function of time for a point along the outer edge of the disk? All right, so let's take a look at that and think about how we would set that up. So in part A, we're just going to use our new kinematic definitions of velocity, acceleration, and displacement. Okay, so we were given the angular velocity. Here we're asked for the angular position. That means we're going to want to integrate. So let's go ahead then and write that omega is d theta dt. I'm going to kind of do a separation of variables here and get my omega dt over here and my d theta over here. Okay, then we'll set up an integral going from omega naught to omega, and then we'll have our expression, which I'll plug in the next step for omega, our time-dependent expression, this one right here. And then we're going to set that equal then to just our integral of d theta from theta naught to the variable theta d theta. Okay, now our theta naught though is going to be defined as 0 because we're just starting from 0 displacement. Okay, so that means that our theta is then going to equal our expression here. We're going to have going from omega naught to omega of negative 1.6 plus 3.2 times t squared dt. Okay, and then we're told that it starts from rest, right? Always crucial information. So we're told it starts from rest. That tells us that our omega naught is none other than 0. So then our expression is basically telling us our constant of integration is 0, is another way to think about it. But here, of course, I've done it with a definite integral. And so that means that our final expression will just be negative 1.6 t and then plus 3.2 divided by 3, which should give us 1.07. All right, so 1.07 times t cubed. Okay. So there we have an expression for our time-dependent angular displacement. This is basically just telling us how many radians are covered in a certain amount of time. So if we wanted to find out how many radians had been displaced after a time of 1 second, then I just plug in 1 second for both of my t's. Now do notice that this has a negative, so there's going to be a point where it's going to cross back over 0. Sorry about that. Okay, so there's going to be a point where it crosses back over 0, and that means that we would have a point where we have 0 angular displacement, because this is angular displacement, not angular distance. This expression right here, right? It's angular displacement. If we wanted angular distance, we'd have to sum up the displacements, both the positive and negative ones. Okay. All right, so then in part B, we're asked for the angular acceleration vector. Well, that's simply going to be the derivative of our given angular velocity vector. So it's just d omega dt. Okay, this one should be very straightforward to calculate. And so we see what we get is just 6.4 t. Okay, so we have a linearly increasing angular acceleration. All right, and then in part C, we're asked for what is the translational acceleration as a function of time. Okay, well, what that would look like is we'll use kind of the expression that I mentioned. So we'd simply have that A is going to be R times alpha squared times omega to the 4th, like so. All right. Oops. There we are. Okay, and then we can just kind of plug it in. We'll leave it, put the numbers in, but not clean it up excessively. So 1.5 meters, and then we'll have our square root, and then we'll put in our 6.4 t squared, and then our negative 1.6 plus 3.2 t squared, and that whole thing to the fourth power inside the root. All right, and that'd be it. So then if we wanted to know, what was the angular acceleration after 1 second again, we could literally just plug in 1 second, and then we get a value, which give us the magnitude of the angular acceleration. It wouldn't give us the angle, right? If we did want the angle, we could say, do an inverse tangent function in order to find the angle relative to either the tangential axis or radial axis and kind of go from there. But you will see that come up in other problems. Okay, so hopefully that example makes sense. Let's go ahead and move to the second part of our practice here, which is a conceptual question. All right, so we'll go through the answers here. So here we're showing a figure of a plot of angular displacement theta for 3 cases of a rotating disk. At what value of time does each disk change direction? Okay, so if we're looking for a change in direction, that's going to be where the slope of the angular displacement, so the slope of theta, changes from negative to positive. Now the slope is obviously changing in value because the slope, is the tangent line, and we have something that looks like a parabola here. But when it changes sign, then we know we have a directional change. All right, so let's color code these. So for the first one, for 1, our change in direction is going to occur at a value of, let's see, so we have our time here, so 0. So I guess at negative 2 seconds by the looks of it. Yeah, so 1, 2. So, oh yeah, those are the labels, yeah. So it'll be at negative 2 seconds. Okay, so apparently we can go before the beginning of time here. Just, of course, it's just relative to wherever our clock started, and this is 2 seconds before our clock started. Okay, and then for the purple one, it looks like we definitely have a change in direction right at 0 seconds. And then for the blue one, we have a change in direction right at 2 seconds. Okay, at what values of time is the angular velocity omega 0? Okay, well the angular velocity represents the tangent line of these graphs, just as if this was graphs of displacement, we would know that the velocity would represent the tangent line. So like right here, right, that's a tangent line. And there where the slope is 0, that means the angular velocity is 0. So it's going to occur right at the point of directional change. So we should get all of these same answers. All right, because directional change corresponds to a momentary 0 value of angular velocity. For each case, is the angular acceleration 0, constant, or non-constant? Well, it's hard to tell, but if we assume they're all parabolas, they are as far as we can tell, then that would correspond to a constant angular acceleration. More on that in just a minute in the next section. So if all graphs are parabolic, then acceleration is a constant. And of course, that's because we would have constant angular acceleration. As we took the antiderivative, that would give us linear angular velocity, and as we took the antiderivative again with respect to time, we would get parabolic angular displacement. Just as with constant acceleration, we had linear velocity change and parabolic position change. Okay, now that is in contrast to the last example, because in this example here, we had an angular velocity that itself was parabolic, which gave us a third order polynomial for displacement and a linear angular acceleration, not a constant angular acceleration, right? But this is not a parabola. Okay. Now again, maybe these aren't either, but as far as we can tell, they are. And then for each case, is the angular acceleration positive or negative? Well, the angular acceleration would represent the curvature. So then alpha is curvature of the theta graph. So with that in mind, we can then simply say that for the green one, we have a positive alpha. For the blue one, we would have a positive alpha as well, because both of those have a positive curvature. And then for the purple displacement, we would have a value of negative alpha, all right, because that has a negative curvature. It's sloped down, or it's curved down. All right. So I'll leave example 2 for your practice. All right. And let's go ahead and stop this video. And then on our next one, we'll talk about the second section, the second half of lecture 18, which covers rotation with constant angular acceleration.